Okay, so welcome to class for, I guess it's Thursday, April 16th. And okay, so items of business today. We need to talk about abstracts, and we need to talk about section 3.3, and we're going to talk a little bit about the concept of what are sometimes called confidence intervals, or particularly for a asymmetric probability distribution. So we'll do those things, probably not in that order. The other thing we need to do is figure out who's presenting on Tuesday. So on Tuesday, we're going to skip section 3.4, and we're going to go over section 3.5, which is talking about multivariate probability distribution functions. So who wants to talk about 3.5?
I can do that, Dr. Nelson.
All right, Blake, all yours. And then we're going to skip to chapter 5, so that'll be fun. Okay, so that was easy. Next item of business. Dylan, why don't you go ahead and tell us the tale of section 3.4? Or 3.3, sorry.
Can I, it says the screen sharing is disabled.
Yeah, I have to turn it on. I always forget that. All right, you should be able to do it now.
Okay. Can you see my cursor also? Cool.
Mhm.
Let's go, I guess, back to the beginning of the section. This section has to do a lot with what Dr. Nelson talked about on Tuesday with these things called moments. And like he also said, just a reminder, the characteristic function is basically just the Fourier transform of the distribution. Here's how we find those things called moments. Just Fourier transform there. And so in the last section, we talked about the first 4 moments, and here we're going to talk about any arbitrary moment, or how to find any arbitrary moment, which is this here. You can also find them. You can find them centered around any point, not just the origin, which is what they're doing here. They're just shifting the graph, and you can find them around also the expected value, which is the central moment. Let's see. I'm not sure if this is really worth talking about, but just some things that are properties of that. The characteristic function, we're coming back to that. They're calling it phi of t. And, excuse me. This is also just, it looks like quantum mechanics, some quantum mechanics stuff. Basically everything, sort of all stuff we sort of know here is just saying that, like, it can be normalized, basically, seems like, in that sort of thing. Properties of it, I don't think they're very, at least, maybe, I don't know if those are important. What exactly is important in this section, but keep going. I think the more interesting part of this section was when it starts to talk about the moments again. And so I think what it is you can find those by taking derivatives and then Taylor expanding. And these are the moments here, which is kind of interesting. see. This I thought sort of looked familiar as well from quantum mechanics, or a little bit of quantum mechanics that we took in modern, or that I've taken in modern. All it's saying is this: if you have a function that's a variable of two independents, so here they have f of z, and z is equal to x plus y, so two independent random variables. You can say the f of z is the characteristic function of the product of g and h. So that kind of reminded me of in quantum when we start talking about like angular momentum, we had the product of, like, we called it like big R, I think, and big theta or something like that. I'm not entirely sure if that's analogous to that, but that's what it reminded me of. Here they just go through a quick proof of that. And so here they say that in the general case is just this thing just means is the product of these. So this is like a summation, but a product. And so cumulants, I wasn't sure if I 100% understood. It seems like they make this other function called k of t, which is the natural log of the characteristic function. And these kappas come out of that. The kappas are what they call cumulants or semivariants. I wasn't 100% sure exactly what they are. We can write the mode or the moments in terms of them. I know that here they do that here. This is the first and second moment. But I'm not entirely sure really what they are exactly. I mean, here it defines them, but I'm not sure like how you get them, like where they would come from. I guess it looks like maybe some sort of expansion, but.
So the real, okay, so there's sort of two things. A lot of this is just stuff about Fourier transforms, right? Like they're just showing you how Fourier transforms work. One thing that you may not have realized is that, so if you scroll up a little bit, yeah, keep going. Yeah, a little more. There you go. Okay, so on the top of page 35 there, it defines a function that's the result of a convolution. So a convolution is, well, it's exactly what's written in that formula right there on the top of 35, right? F of z equals the integral of g of x times h of z minus x over x, right? So when you do the integral, the variable x drops out. And basically what a convolution is saying, you basically add up all of you take two functions, right? And then you sort of like shift them relative to each other and add up the integral of the functions with the overlap, right? So for example, if h were a delta function, then your f of z would be the same as g. Does that make sense?
Yeah.
Right, because it would just pick out each, you have some function, right? And you'd come by and you'd pick out one value. So from a computational standpoint, a convolution is a nightmare, right? Because you have to do the integral for every different value of z. So it's going to be a lot of integrals. And they're pointing out this nice feature that if you take the Fourier transform of the two functions, g and h, the convolution is just the products of the functions after you've taken the Fourier transform. So if you scroll down just a little bit, we'll see that. Yeah, right there, the 3.25. So all it's saying is, so frustratingly they wrote it a different way, right? But basically what they're saying is that the phis are the Fourier transforms of f, g, and h, right? And what
Yeah.
they're saying is instead of having to do that convolution, you can just do the Fourier transforms of g and h and just multiply the Fourier transforms together and you'll get the Fourier transform of f. So instead of having to do a convolution, you just get to do multiplication.
Yeah, and they said that this Fourier transform is uniquely related to the moments, and if you have all the moments to the nth order are the same in two different cases, then they're identical. And these characteristic functions are unique to those moments. So they said sometimes it's easier to find this characteristic function than it is to find the moments, which was the importance of that.
Right.
Which is interesting.
And the reason this all works is because when you take a Fourier transform, right? So let's scroll back up, maybe to let's see here. What page do I want? Like on page 32.
32.
So the very beginning of the section. Okay, so they show you these moments, right? And the moments are just, let's see, can I write on stuff? I think I can somehow.
Harmon can stamp arrows on your stuff.
I know. Harmon can stamp arrows. Why can't I write on stuff? Okay, I can't figure out how to write on stuff. Okay, but anyway, the if you look at the definition of the moment, right? That first formula under definition, right? It's just the integral of x to the n times f of x, right? From negative infinity to positive infinity. Okay? If you look at a Fourier transform, that's exactly the formula for a Fourier transform if instead of x to the n, see, there you go. How did you make an arrow, Sean?
Okay, so what you do is you go up to view options and go down to annotate.
Annotate. Ah, there we go.
Get all of the tools, all of the
cool. So I can draw. Sweet. Okay, so what I'm talking about here is this formula. Okay. If you took that formula and instead of having x to the n in there, you had e to the I t. That's terrible. Okay, if instead of x to the n, you put e to the it in there, then now all of a sudden itx. Now all of a sudden this is a Fourier transform, right? Because that's how you take a Fourier transform. Is instead of multiplying it by x to the n, you multiply it by e to the itx. Okay, so here's the cool thing. What's the Fourier, or what's the Taylor expansion for the exponential?
X to the nth power over n factorial.
Right, it's the sum of them, right?
Yeah.
So what you're doing here is you're actually calculating all of the moments. They just have an extra I on them, and t here plays the role of n. Okay? So by plugging in different values of t equals 1, 2, 3, 4, you get the moments. Which is kind of weird, right? Because this isn't the way we're used to thinking about Fourier transforms. We're used to thinking about Fourier transforms as having something to do with like sine waves, right?
Yeah.
But in this case, what this is telling us is that the fundamental of a probability distribution function is its mean. And the first overtone is its standard deviation. And what is that? I don't even know what that means, but mathematically it works, right?
That's crazy.
Yeah, it's kind of clever.
Yeah, I would never think about Fourier transforms telling us about anything about statistics of probability distribution, or
right.
Yeah.
But it actually works. If we actually take the Fourier transform of our probability distribution function, the coefficients are related to the moments of our distribution, right? Which is just kind of crazy.
Yeah,
and
I guess another.
Go ahead.
Sorry. I was gonna say I was sort of gonna change that. I didn't know. I never like realized that the Fourier transform was a unique like solution. I guess thinking about it in terms of like waves, sine waves and stuff. If you had some random wave, I didn't know it was you. There was only one solution to get that would make up that that pattern, that sort of wave pattern. Is that true? It seems like that's how it was with they were talking about with this, is that those moments are going to be uniquely characterized by this characteristic function.
Yes.
So it's the case where if you have a wave, some random wave, it can only be made up from one specific, variation or whatever on cosines and sines.
Right, and that's absolutely true. Usually we don't think of it that way because we're interested in the amplitude, not the phase. But remember, a Fourier transform has both pieces. It has the amplitude and the phase embedded in it. And if you know those two things, the amplitude and phase together, that tells you what you're going to get. Now, there's one more trick to this. Why do they take the derivative? So let me, if I I'll clear my stuff here. Okay, go ahead. If you go down here, when it talks about it, right, it says you take the derivative.
Yeah, where is it? There we go.
Right. So they take the derivative and they say, oh yeah, there you go, we got the derivative. Why do they take the derivative? Any thoughts?
To get rid of the integral?
Well, it doesn't get rid of the integral because remember the integral is over x and they're taking the derivative with respect to t. So let's see if I can draw this. It might help me if I make my screen bigger.
Well, the derivative basically tells you the derivatives are how you build the Taylor expansion, right?
Right. But so here's the cool thing, right? Okay, let me see if I can highlight this. There you go. Okay, so look right here. When you've got your Fourier transform, you take the derivative of it. The derivative is with respect to t, but the integral is with respect to x. So the derivative can move right through, and it can hit this e to the I tx. When we take the derivative n times, all we do is get a whole bunch of ix's, right? And then when because each time we take a derivative with respect to t, all we do is we hit that e to the I tx, and the derivative of e to the I tx with respect to t is just ix times e to the I tx, right?
Yeah.
So the derivative just comes in here and generates all these ix's to the n power. Okay? And then if we evaluate that at 0, when t equals 0, that kills the e to the I tx. And now this is exactly the formula for our moments. And so all it is I to the n times our nth moment. Okay?
Yeah,
So go ahead.
Does that mean, so I thought, for some reason, I thought it was that those terms in the expansion, each one was, the first term was the first moment, second term was the second moment. Do you have to take a derivative to whatever moment you're trying to get to? So like the nth moment, do you have to go up to the nth derivative?
Yes. Here's the thing. So you're absolutely right. You could get them by just looking at the terms, right? Taking the Fourier transform and looking at the terms. The reason that they do this is because what this does is it isolates the terms, right? Because taking the derivative, so think of the Fourier series. Each time you take a derivative, you kill the constant term, right? And you decrease the power on every subsequent term by 1. So if I take n derivatives, what I'm doing is wiping out the first n minus 1 terms and leaving the nth term as my new constant. And then when I plug in t equals 0, that kills everything except the constant term. So this is just a clever way of manipulating things. Now, in practice, is this actually easier than calculating our moments using just taking a bunch of integrals? Well, sometimes, right? It actually happens a lot in optics because I'm not sure if you guys have covered this in optics, but optical elements, often certain types of optical elements like focusing mirrors actually effectively take, and focusing mirrors, slits, some of these things, effectively take the Fourier transform of an object. So for example, a slit, right? A single slit is a top hat function, right? It's just let me go over to my little document camera thing and I can draw this thing. Oh, I got to plug it in.
I guess it makes sense too, because I mean, in optics, lasers are just a Gaussian, right? And so we can, by taking Fourier transforms, it means we can find, what you're really doing is finding all these things about that Gaussian curve.
Right. Okay, so do you want to stop sharing for a minute and I'll write this up over here?
Yeah.
Okay, so what we're saying here, okay, so let's imagine I've got a slit, right, with some width, and then I'm going to look at the pattern that comes out over here, okay? This slit is effectively a Fourier transform. If we think about the intensity of the light coming through the slit, right? If I graph the intensity of the light at the slit, right, as a function of position, it's going to look like this, right?
Yeah.
Okay, all you optics folks, what does the diffraction pattern look like over here? So this is the intensity there. What about the intensity on the back?
Gaussian?
Normal distribution.
What does it look like?
I think Bjorn was saying Gaussian. I was thinking it was just going to be a normal distribution.
Well, Gaussian and normal are the same thing. Does it really?
It's a sinc function.
It's a sinc function. Blake is absolutely right. It's a sinc function. What is a sinc function, Blake?
Sine of x over x.
Why is it a sinc function?
Because that's the Fourier transform of a single slit.
Yes, it is. It is the Fourier transform. So it's going to look like, it's actually going to look like a sinc squared, right?
Yeah.
But it's going to do like this kind of a thing, right? and you're going to get an interference pattern. So that's so these Fourier the point here is that these Fourier transforms pop up all over the place, right? And so sometimes when it's actually easier to measure the Fourier transform of what you want than it is to measure what you want. And so going backwards, you can either just invert the Fourier transform, but sometimes all you want is the moments of the distribution, right? Mean, standard deviation. And you can get them from the Fourier transform is basically what we're showing here today. All right, questions, comments?
It's interesting too, because can't you, like, I'm just thinking of like the whole frog thing that I did. You know, doing a Fourier transform, that tells you, you were talking about the amplitude and the phase as well. And so I guess it makes perfect sense. I'm sort of going back to what we were talking about earlier about how these things are unique. That how you can use that to characterize the your light wave as well.
Yep. Okay. We spent more time on this than I had actually planned, but that's okay because it's fun. Good job, Dylan. Well done. I'll clap for you. Yay, clapping. All right. The one other thing I wanted to talk about today is, before we get to abstracts, is I wanted to talk about confidence intervals. So let me share my screen. Nope, I want to click that thing. Okay, so if we go back to our Monopoly example, right? And we run the thing, we get a probability distribution function that looks like this, right? And we found out earlier, right, we calculated the mean and we calculated the standard deviation, and we said that the average move is 8.3 plus or minus 4.1 spaces, right? That actually doesn't seem to characterize our distribution very well, right? Because while it's true that that's the standard deviation, our you know, the high end here falls off much more slowly than the low end, right? And so sometimes it's not actually the most useful thing to say what's our mean and standard deviation. Sometimes it's more useful, so saying 8.3 plus or minus 4.1 spaces maybe isn't the most useful thing. What might be more interesting is to say, what are the most probable ways you can get 68% of the distribution? Okay? And the answer to that is conceptually very simple and in practice slightly complicated. Okay? We're going to take the probability of the mean, right? Which in our case is about, I don't know, a little 11.5%. And then we're going to just add the largest neighbor to that. And we're just going to keep going until we get to 68% of our probability distribution function, right? So in this case, we would build this by saying, okay, we take our probability of rolling an 8, we add to it the probability of rolling a 7, which is actually the most likely thing to happen, right? And then we're going to go from that, we're going to add the probability of rolling a 9. And then to that, we're going to add the probability of rolling a 6. And then to that, we're going to add the probability of rolling a 5. And sooner or later, we'll get to 68%. Now, here's the reason why we're doing this. We're doing this because what we'll have at the end is going to be an asymmetric confidence interval. We'll be able to say that you have a 68% chance of rolling between, say, a 4 and an 11. Instead of saying, oh, it's 8 plus or minus 4, right? We'll actually be able to say that your confidence interval is bigger on one side than it is on the other. Okay? So you will sometimes see this in papers where people will say that the uncertainty is, 5 plus 2 minus 3. meters, right? What they're doing there is they've calculated, instead of just calculating a mean and a standard deviation, they've calculated what's often referred to as a confidence interval. Okay, so let's show how we would actually program this thing. If I come over here to do this, the first thing I need to know is I need to know where the mean is. So I can do that by just using the argmin function in a clever way. I want the argmin of where the absolute value of my my roll bins, that's the x on the graph I just showed, right? Minus the mean, right? So I want the minimum of that. Okay? If I take the minimum of the absolute value, that gives me the value closest to 0, right? So the value where roll bins, which is our x-axis on our plot, minus the mean is closest to 0. And if I run the thing, we will find out that sure enough, it gives us our mean location is at 5, which if I look at the 5th bin in our rolls, right, I see that the 5th one is 8, which sure enough is the closest value to the one I want. Okay, so now I know where my mean is. Now I need to calculate the area under the curve, right? So we could call this like the probability or total probability, right? And we want to go adding things to this until it gets bigger than some value. So I'm going to just, to start off, make my total probability equal to my PDF at mean lock, the mean location. Okay. And then I have to pick what my probability is that I want to stop doing this at, right? So a standard deviation traditionally is 68%, right? If it's a normal distribution, when you do the standard deviation, you get 68% of your data. So let's do it at 68%. So I want target probability to be 0.68, okay? And then I'm going to, eventually I'm going to get to a while loop here. I'm going to do a while our total probability is less than our target probability. Okay, now I have to go through and figure out how to do the logic I was describing earlier, where I want to look at the two neighbors to my mean, take the biggest one, and add it to my total probability. And then look at the two neighbors to that new region and add the biggest one to my total probability. And just keep doing that until I get bigger than 0.68, bigger than my target. Okay. So here's how I'm going to do this. I decided to do a while loop. You could probably do this with a for loop too, but I'm going to do it with a while loop. And I'm going to say step plus equals 0 and step minus equals 0, because I haven't stepped in either the positive or negative direction yet. And as soon as I get in, I need to do a check. If PDF sub mean lock plus step positive plus 1. So that's going to be one space over to the positive side of my current region, right? If that is greater than PDF sub mean locks minus step minus 1, that means if this is true, that means the positive side is bigger. So I want to add that in. So I'm going to say step P plus equals 1 and total probability plus equals PDF sub mean, oh, I said mean locks. It should just be mean lock. Mean lock plus step P. And I already added 1 to it, so I don't have to do the +1, right? So it's just saying add your neighbor. Okay, now I've got to do the else. If that wasn't true, that means the minus side was bigger. And so my PDF or my step minus or plus equals 1. And my total probability plus equals PDF sub mean lock minus step M. Okay, does this make sense what we're doing here in this loop? This idea that what we're doing is we're just grabbing the biggest side, whichever side that is, and we keep adding it. Okay, so now when we get done with this, we're going to say we're going to print that our confidence interval is from roll bins sub mean lock minus step M to roll comma to roll bins sub mean lock plus step P, right? And if we go ahead and run this thing, let's see if it actually works. Okay, so what this told us is that our actual confidence interval, right, is from 5 to 10. And we could look in here, if we look over here, we'll see that the total probability there is 69%. So 69% of the rolls are between 5 and 10. Now that's different than looking at the standard deviation, right? The standard deviation said that our range was between, let's see, average move minus standard deviation would be 4.1 something minus, or on the small side, to 12.5 on the plus side, right? So let's see if I can plot this. Let's come up here. And we're going to add some stuff to this plot. So we'll make another one. We'll call this confidence intervals. And we're going to make our histogram again, right? And we'll make red lines for our mean and standard deviation. Oh wait, V lines, I can give it more than one thing. I can give it average move, minus, it's mean move is actually what I called it. Mean move minus, I gotta do the square root of variance move, comma, mean move, plus NP dot square root, variance move. Close that. Okay, let's see if that works. Let me run the thing and see if it, it didn't like that. What did I do wrong? Oh, I had two M's. My M key is sticky. Oh. I don't give it the line style. Okay, so there's our standard. That's what our mean and standard deviation would say, right? On top of that, let's print our, let's put our confidence interval that we just calculated. So we're going to do roll bins sub mean lock plus step P, comma, and then we'll just grab this whole thing again. And we're going to do minus step M, and we'll do all the same stuff for plotting, except for we'll make them blue. Okay, so now what this is going to show us, if I, oh, what did I do wrong? Am I missing something? Oh. Oh, V lines. Okay, did you make me plots? There they are. Now, blue's not a great choice. But you can see that the confidence interval is actually very different than the standard deviation, right? How is it different?
It's asymmetric.
It's very asymmetric, right? What else?
It's also like not as wide.
Yeah. It turns out that if we stated this, right, so we'd actually be, if we use the mean and standard deviation here, we would actually be giving the wrong impression, because scientists are used to thinking of standard deviation as, oh, that's like 68% of possibilities, right? And that's true for a normal or a Gaussian distribution. But it's not true here, right? 68% of possibilities, it turns out, is all contained in this central bump, right? And so this is this distribution, at least in the high end, is very centrally confined. Okay, you can see that this obviously gets into trouble if we wanted to do a 2 sigma confidence interval, right? So if we did 2 standard deviations, well, 2 standard deviations, remember the average is 5.5 and the mean is 4.1. So 2 standard deviations would be at a roll of point, like actually almost exactly 0, right? Which obviously isn't a possibility. The smallest move you can possibly make is 3 spaces. So this idea that 2 standard deviations would give us 95% of possibilities is terribly wrong, right? Because it's actually off the bottom of the distribution. So what would be much more useful would be to come in here and say, okay, let's see what happens if I go to 9.5 and I run the thing. Ah, there's where 95% of my values are, right? 95% of my values are going to be between 3 and 17.
So just to clarify, the blue lines are the confidence intervals, right?
Yes, the blue lines are the confidence intervals. The red lines are the standard deviation. So let me actually, so we're comparing apples to apples. Let's multiply the square root or the standard deviations by 2, right? And if we plotted this thing, we'd see that this is what your this standard deviation would tell you is the range where you're going to get 95% of all values. Whereas the blue is the actual confidence interval that tells you that, right? Now, you'll notice a couple of things, right? The blue is still narrower, right? But only slightly on the positive side. Actually, it's slightly wider on the positive side. It's slightly narrower, it's a lot narrower on the negative side because this never happens, right? You can't possibly roll less than 3. The probability of rolling less than 3 is 0. So we'll never move the confidence interval below 3. We'll just keep moving it up to add in more and more of your options. So does that make sense? So when you're dealing with data, right, these complicated distributions that come out of data, and that data can be experimental data, it can be simulated data, right? Oftentimes it is more useful to talk about these confidence intervals, right, and get the idea of what the asymmetry is than it is to talk about the actual values. Now, how we would write that, okay, what we would actually do is when we talk about our confidence interval, we would say that we'd say 95% of moves will be, and then we would say something like mean lock, roll bins sub mean lock, comma, plus, and then we can give it our step plus minus our step minus. So that would be how we'd actually report it. We'd say 95% of moves will be 8 plus 10 or minus 5, right? And oftentimes in scientific notation, the way this gets written, let me close these and just write it on the screen, is we would say that the average move is 8 plus 10 minus 5. Okay? Does that make sense? So you'll see that in papers. You'll see where people will write, instead of saying like 8 plus or minus whatever, they will say 8 plus 10 minus 5. And that's just saying that what they did is they took into account the fact that their probability distribution was asymmetric. And instead of just reporting the standard deviation, they've actually done the legwork to figure out what actually the confidence interval is. Okay. This has taken way more time than I would have guessed. It's 10:22 right now. How are we feeling about abstracts?
I mean, you know, we have a draft.
We have a draft that that we are ready for you to absolutely destroy, Dr. Nelson.
Okay. Let's see, Blake. I think you're the only person here from the Canopy group. How are you guys feeling about yours?
Yeah, I mean, I'm feeling all right about it. Herman and I are just still working on it.
Okay.
I mean, it looks like Harmon is here.
Is Harmon here?
Input.
Yeah.
Oh, hey, Harmon.
Hey, Herman.
Hey.
I should have guessed when I see a hippopotamus pop up in the participants window. I'll stop sharing my screen. Okay. So let's see. And then Dylan, Josh, and Leonard, how are you guys feeling?
Pretty good, I think.
Yeah.
Okay, so why don't we do this? Instead of trying to do this live with everybody, I thought it might be kind of nice to go over them as a group and sort of talk about them. But let's not do that because I've already talked for like an hour. I've got all of your documents shared with me. So I will go over them and I probably won't change things. I'll probably make comments or suggestions. And then if you guys can look over them sometime between now and Friday and, respond, make changes, I'll give them one more look over on Monday. And then I'll shoot out a mass email sometime Monday about submitting, and I'll say, go, yes, submit, and we'll go ahead and submit.
Will we be able to give our say we don't want to have a poster, additional poster? Could we also do PowerPoint or some sort of presentation that could be presented for this? Are they doing anything cool because it's going to be all online?
So they have given us very little information about how they're actually presenting things. I would like you guys to actually make posters because I think the posters are going to be things that are useful for you outside of just this poster session. I don't really know how they're going to present it. I don't know if it's just going to be people downloading PDFs of posters. I know they will give us the chance to upload a video of people presenting their posters. But I don't really know. So let's do posters. Make an actual poster. You can make it on Google Slides, and that way everybody can fiddle. And is there any of the groups have somebody who hasn't used Google Slides to make a poster at some point in their life? Let me ask it the other way. Has anybody used Google Slides to make a poster at some point in their life?
Yeah, I've done that before.
I've done that as well.
Okay. So the Galaxy people and the Canopy Wave people are okay. Anybody from the from the Salestronaut?
Yeah, I have before.
Okay. So good. Then if you know how to do this, go ahead and make it on Google Slides, right? It's easy. You just make a slide and then you tell it its physical dimensions are 3 feet by 4 feet, right? And then the thing to remember is your font sizes are your sort of touchstone, right? So a 12-point font is still a 12-point font, even though it will look tiny once you've made a 3 foot by 4 foot slide, right? But choose your fonts and lay out your poster. Sound good?
I have a question. Since this is like an online poster, would it be weird to put like a little simulation in there?
You mean like a video?
Yeah.
Yeah, put it in.
Yeah.
I have no idea how we're going to present these things, right? But sure, put it in. Worst case scenario, you put the video in. They just want a PDF. Fine, we'll just give them the PDF and it'll have a frame from the video, and you can put a little note in the caption that says that this is available as a video and then give somebody the link to it, right? I assume you're just going to put it on YouTube, right?
Yeah, sure.
Okay, yeah. Or whatever. Put it on it, make a GIF out of it or something. I don't care.
Cool.
And if we if we have videos showing us presenting the poster as well, then that video will have the poster video on it as well.
Right. Okay, I'm hoping we get more guidance on exactly what they're going to do and how they're going to do it. But as of right now, this is all we know. So, okay, so the goal is by Friday to have worked amongst yourselves, get yourselves in a happy place with abstracts. I will have a look at them Friday, give you any feedback, and then try to get that done over the weekend or Monday morning. And then Monday midday, I'll have one more look at them, give everybody the thumbs up, and you can submit.
Sweet.
All right.
Sounds good.
Okay, well, let's call that class for today, and then we will pick this back up again Tuesday.